So we can start with the simple equivalent circuit of an LC oscillator, which we had already discussed. It has an inductor and capacitor in parallel, forming LC resonator. Then a parallel resistor which is modeling the loss in the resonator. And to compensate this loss, we connect some active circuit which has an effective resistance of -R. And we take this voltage as the output. In addition to this, to understand the characteristics of this LC oscillator, we had connected a current source, and this current source can provide an impulse current which will add some initial charge to this capacitor. And then this capacitor will discharge over time through this oscillator circuit, resulting in the output voltage. This is the equivalent circuit of LC oscillator. Okay, so in this equivalent circuit, if we want to understand the phase noise in the output voltage, we can try to find out what is the transfer function from this input current source to the phase of the output voltage. And then we can replace this input current source with the equivalent noise sources to find the phase noise in the output. So we are interested in VO by in. Let's call it ZLC. And we want to understand how this transfer function VO by in will look like around the resonant frequency, because the phase noise will appear as some side skirts at a delta omega offset from the oscillation frequency, which in our case is going to be the resonant frequency of this oscillator. So if we look at the circuit, we can see that in steady state, this negative R is completely compensating the loss in the resonator. So if we want to understand what is the impedance at a close frequency offset from the resonant frequency, then the equivalent circuit, we can see that this R and negative R will just cancel each other. So we will be having just this LC. This L and C in V0. And we are interested in the VO by In, or the impedance of this resonator at frequency omega naught plus delta omega. F R and minus R cancel each other. And we want to find the impedance of this transfer function and delta omega offset to find phase noise at delta omega offset from omega naught. Here we can see that since it's a parallel combination of L and C, we can simply find the admittance of this parallel combination at delta omega offset, and later on we can take inverse to find the impedance. So this YLC at omega naught plus delta omega is going to be 1 by j omega naught plus delta omega L plus j omega naught plus delta omega C is equal to 1 minus omega naught plus delta omega whole square LC divided by j omega naught plus delta omega L. Now if we expand this omega naught plus delta omega square, we are going to get omega naught square plus delta omega square plus 2 omega naught delta omega 2 LC divided by j omega naught plus delta omega 2L. It implies that the admittance at delta omega offset can be approximated to 1 minus omega naught square plus 2 omega naught delta omega LC by j omega naught L. So here we are assuming that this delta omega is much smaller than omega naught. So if we compare these three terms, the delta omega square can be easily ignored. And similarly in the denominator, we can ignore delta omega and comparing to omega naught. Assuming delta omega is much smaller than omega naught, and which is also true because we are looking at a offset frequency of delta omega, which is going to be at max maybe few tens of megahertz, whereas this omega naught is going to be in gigahertz. We can see that this admittance is equal to 1 minus this omega naught square into LC minus 2 omega naught delta omega LC divided by j omega naught L equal to, so this omega naught square LC will become 1. So these two will cancel. Omega naught is equal to 1 by root over LC. See that this is becoming minus 2 omega naught delta omega LC divided by j omega naught L. Equal to j delta omega 2C. You can see that at frequency slightly above the resonant frequency, admittance will be completely capacitive in nature. And here we can see that the equivalent circuit at a delta omega offset can be drawn as just a single capacitor of value 2C. So we can say that omega naught plus delta omega is equivalent to, as if you have a capacitor 2C which is excited by source at delta omega. So resonator at omega naught plus delta omega is same as 2C capacitor at delta omega. Now we have got this idea about the equivalent circuit. Now very easily we can find what is going to be the effect of any current source in parallel to this resonator at delta omega offset. So now let's say a noise source is connected across this LC oscillator. And we are interested in finding out what will be the output noise at omega naught plus delta omega. Then we can just replace this LC circuit with an equivalent capacitance. So we can directly write this PSD of the output voltage noise at omega naught plus delta omega as the current noise PSD multiplied by the impedance of this capacitor at delta omega. So the impedance of this capacitor at delta omega is 1 by J delta omega 2C. We are going to take a square of this magnitude. So it is going to be equal to the current noise PSD multiplied by 1 by delta omega square for C square. Now let's take a case when this current noise is coming because of the resistance which was connected in parallel to the oscillator. So if we connect the current noise due to this parallel resistor, IN square equal to 4 kT by R noise due to R. Here we are ignoring the noise due to this active circuitry. Then we can find the output noise PSD to be equal to 4 kT by R into 1 by 4 delta omega square into C square. And this can be rewritten as kT by delta omega square. And we also know that the Q of this tank without any active circuit is equal to omega naught CR. We are going to replace C with Q tank by omega naught R. So we are going to get omega naught square R square divided by Q square. This was already there. This is equal to kT into R by Q square omega naught by delta omega whole square. Here this is Q tank. So we understand that this is the voltage noise PSD at the output of the oscillator, and the oscillator is already oscillating with some amplitude. So to understand how this additive voltage noise is going to affect the phase noise of the oscillator, let us quickly find out a useful result which relates the effect of additive noise to the phase noise. This is the output voltage noise PSD when oscillator is already oscillating at omega naught. So let us try to understand the effect of such phase noise by looking at the phasor of the output voltage. So let's say this is the phasor of output voltage looking at omega naught, having a phase theta and an amplitude A. Now if noise is added to phasor, then that noise will have its own magnitude and phase. So the net result is going to be a vector sum of this signal which is already present with the noise. So to understand the impact of this noise onto the phase, we can resolve this noise into two components. One component along the direction of the signal, another component in quadrature with the signal. So this is Vn, and let's call this guy as Vni, the other one as Vnq. So now looking at these two components of Vn, we can easily see that this Vni component is going to directly affect the amplitude of the signal. So this component we can say will contribute to the amplitude noise. Whereas if you look at this Vnq, then due to the Vnq, the net output is going to look like this. Now we can see that this output voltage will be having some extra phase shift of phi, and this phi is going to appear as the phase noise. This Vnq will directly result in phase noise, whereas this Vni will directly result in the amplitude noise. We are trying to understand the effect of additive noise on oscillator phase noise. This is the oscillator clean output. Vn is the additive voltage noise, and we can now easily see that this phi is going to be almost equal to this Vnq divided by amplitude of the clean signal, which is A in our case. This is going to be equal to Vnq divided by A. And if we want to find out the PSD of this phi, this is going to be equal to PSD of V and Q divided by the signal power, which will be A square by 2. This is the PSD of phase noise. So we can directly see that this V and Q will result in the phase noise at the oscillator output. So if we know the PSD of Vn, we can make an estimate of the PSD of V and Q, as we know that the PSD of Vn is going to be equal to PSD of V and Q plus PSD of V and I. So part of the additive voltage noise will contribute to phase noise, and part of it will contribute to the amplitude noise. Results in phase noise, results in amplitude noise. Here we are going to make an assumption, and we will say that the total power in the additive voltage noise will be equally distributed to the phase noise and the amplitude noise using equipartition theorem. Since the additive noise can only result these two components, so we will just say that half of the power is into the phase noise, half of the power is to the amplitude noise. We will consider P and Q square to be equal to half of Vn square. Now from here we can find out the PSD of the phase noise. So we know that the S phi n is going to be equal to half of the PSD of the additive voltage noise. In our case, VON square divided by the signal power. So this is going to be equal to half of VON square, which is KT R by Q square omega naught by delta omega whole square into 1 by A square by 2. Here we can see that this A square by 2 along with this R will be the output signal power or output carrier power. So we can rewrite this as half KT by P signal into 1 by Q. So here it is Q tank square omega naught by delta omega whole square. Here we are considering signal power to be equal to A square by 2R. And this S phi n at the offset delta omega is also denoted as L delta omega with 10 log of the entire expression. So rewriting it as 2 kT by signal power 2 omega naught divided by 2 Q tank 1 by delta omega whole square. So here we can see that phase noise I expected is going to be inversely proportional to the signal power. At the same time, here we can see that the Q tank also plays an important role in deciding the oscillator phase noise. So if we start with a tank which already has a very high Q, its phase noise is going to be lower. Also, as the frequency offset increases, the phase noise is going to reduce as per this relationship. And if you look at the oscillation frequency, then we can see that higher will be the oscillation frequency, higher will be the phase noise. Because for the same amount of shift in the zero crossing at a higher frequency, it corresponds to a higher phase change. So this is the result of an LC oscillator phase noise due to a flat thermal noise. And one more point here is that we have assumed that the entire oscillator circuit is linear as well as time invariant. The above analysis assumes LTI for oscillator as well as we are also assuming that the noise is stationary in the sense that the statistics of the noise is not changing with time. Whereas in reality, we know that in an oscillator, because of the large signal behavior, the transconductance of the MOSFETs is going to change. So the statistics of the noise may not be assumed to be stationary under those conditions. Noise is stationary. So if we plot this phase noise as a function of frequency offset, we can see that we can convert this L delta omega into L delta F, get this relationship to KT by P sig F naught by Q tank into 1 by delta F whole square. We're plotting in dVc per hertz. So if we look at this relationship, then we can see that the phase noise is reducing with delta F, and in this log scale, its slope is going to be equal to -20 dB per decade.